Physics of Time Asymmetry, published in 1974, I think it was, dealt with the question of time's arrow, the asymmetry of time, the distinction between past and future. What is it that gives our universe that unidirectionality? Where does that come from? And that's been a constant theme in my own research, which has covered many, many fields of physics and beyond physics in recent years. And I could touch on that. But we decided that it would be good to talk about the subject of the beginning and end of time. So that sounds something fairly alarming. Can time come to an end, and what does that mean? Well, I'd like to give you the latest thinking on that from the perspective of modern physics and cosmology. So let me start with a statement that won't surprise you, which has to do with the origin of the universe, the so-called Big Bang, which in the last decade or so we've been able to position rather precisely in time. We know it was 13.8 billion years ago. When I was a student, all you could say was, well, it was billions of years ago, maybe 10, maybe 20. Nobody really knew, but we can be quite precise about that now. The measurements are out there. The issue with the Big Bang, cosmologists agreed that that represents the origin of the universe, at least as we know it. But what we're all interested in is, was that also the beginning of space and time, or was there something before the Big Bang? And if there was, what was it? And again, we'd like to know what caused the Big Bang. So these are questions that come up again and again in modern physics and cosmology, and I'll give you some idea of the answers that are out there. But before we do that, let me, and see, I hope I'm pronouncing that approximately correct, gave us a wonderful introduction to the notion of, well, the different notions of time, and in particular Newton's concept of the clockwork universe of time flowing equably without relation to anything external. And so for Newton, the time had no beginning or end. There was just this sort of gigantic cosmic clockwork that ticked over and kept perfect time in some sense. So for Newton, time was eternal. But the word eternity, we've heard a lot already about time and eternity. So to a physicist, eternity means two quite different things. One is time without end, that is infinite time, so just time as we might know it or measure it, but going on forever and ever in both directions. And eternity also has the meaning of being outside of time altogether. It's a different sort of meaning, and the latter, for example, I would say mathematics is eternal. So the statement 11 is a prime number bears no relation to time, it's simply true, and whether time exists or not. So it's outside of time. And when it comes to theology, of course, we would like to know, is God within time, or outside of time, or somehow both? But I'll come back to that later. For Newton, time had no beginning, so the universe had always been there. But that's a problem, a very obvious problem, because, as we know, nothing really lasts forever. And if we take a good example of that, our sun. It seems to be eternal, it doesn't change much, it's dependable, it rises every day, it goes on shining, but we know enough physics now to realize this can't literally go on forever. I took the trouble to compute the fuel bill for the sun there, that was in year $2,000, and you see it's squandering a lot of energy. Most of that energy pours out into space, about 2 billionths of it hits the Earth and does some good, so to speak. Most of it is lost into the depths of space. And of course, that fuel bill has to be paid somehow. The sun doesn't have an inexhaustible supply of fuel. It's burning through its hydrogen, which is burning not in the striking a match sense, but burning in the nuclear sense. It's a thermonuclear reactor that is gobbling up its fuel at a prodigious rate. And one day, it will run out of fuel. and that'll be bad news. But don't worry too much, because it won't run out of fuel for some billions of years, although in about another 800 million years, the sun will start to struggle, and it will actually swell up and become cooler surface temperature, but emit more radiation overall, and it will probably engulf the Earth. It will certainly vaporize the Earth. So we've got about 800 million years to plan our escape. But the point I'm trying to make is that stars, the sun won't go on burning forever, so it can't have been there forever. It can't have been just burning away forever and ever. And what's true of that, of the sun, is true of the stars. And we see stars literally in their death throes with pictures like this. So the little spot at the bottom is actually not a galaxy. You see the galaxy, which will typically have several hundred billion stars, like our Milky Way. From time to time, a star will explode and come to an end. I mean, that's the end of the star. And you see one doing that there. It's called a supernova. And not all stars end their days as a supernova, but some do. And there's one that is very famous for those who are interested in the history of astronomy. In the year 1054, Chinese astronomers noted what they called a guest star, a new star, appearing in the constellation that we call the Crab. And if you look there today, what you see is this ragged cloud of gas. The center of that cloud is a neutron star, which is the remnant of the core of the star that exploded. Didn't explode in 1054 because it's many, many light years away, but it was seen to explode in 1054. So stars don't go on forever, and the bigger ones end their days like this. The smaller ones a bit differently. I don't have time to explain it all. However, it's not quite true, but almost, that for every star that dies, another one is born. And this is an image of a system. This is very recent. It's only in the last few years it's been possible to form images of star systems, planetary systems, because we now know that when stars form, they tend to form planets around them. And you see that the planetary nebula there. This particular picture was taken at an interesting observatory called ALMA, the Atacama Large Millimeter Array, which is about 5,000 meters high in the Andes. I went there, I've been there twice actually, and you have to have oxygen to go up to where the telescopes are. I gave a lecture at base camp, which is probably about 3,000 meters, maybe a little more, I think probably 4,000 meters actually. It was the highest lecture I've ever given. I managed to accomplish it without fainting. The detail on the right is the scale of the solar system. So you see we're dealing with something very much like the solar system, which is 4.5 billion years old, so that's fairly old, but this is a new one. But the problem is that there's, again, not an inexhaustible supply of stuff from which new stars might form. So as the old stars die one by one, the rate of formation of stars, of new stars, gets less and less, and eventually it's all going to run out. And so this is a picture of a typical galaxy. Our Milky Way might look like this. And over the coming, say, tens of billions of years, it will inevitably dim. Now, let me talk a little bit about the evidence for Big Bang, because people often say, well, is it just a theory? But it amounts to more than that. The most direct evidence is that the universe is expanding. You've probably heard about that. This is the gentleman who didn't actually discover it, but he got the credit for it. This is Edwin Hubble. Interesting that he started his career as a lawyer, and then saw the light, literally, and switched to becoming an astronomer. He's almost never seen without his pipe. But what he found, or what he championed, is the notion that when you look at a galaxy like that, if it's a long way away, its light is shifted towards the red end of the spectrum, is reddened, and that the amount of reddening is proportional to the distance. And the best explanation of that is that the whole universe is expanding. And people get confused because they think, well, is the universe the explosion of a lump of something from from a particular point in space? No, is the answer. It's really best thought of as the expansion of, or swelling of space itself. The gaps, the space between the galaxies gets more and more every day. So every day around our Milky Way galaxy, more space appears, or space stretches, if you like. So everything is moving away from everything else. There's no center or no edge. There's the Hubble Space Telescope, by the way, named after Edwin Hubble. And today, telescopes like that can form images. This is one called the Hubble Deep Field. Every spot you see on there is actually a galaxy, not a star, with one or two exceptions. So we know now there's hundreds of billions of stars per galaxy and hundreds of billions of galaxies, so out to the distance, maximum distance that we can probe, which is incidentally the distance that light has travelled since the Big Bang. We can't see beyond 13.8 billion light years because light hasn't had a chance to reach us from those regions yet. If it were just the expansion of the universe, one could question, as indeed my early mentor, Fred Hoyle, questioned whether there had to be a Big Bang. You could have expansion without a Big Bang. But very strong confirmation came in the mid-1960s. The afterglow of the heat from the Big Bang was detected. If you squash something, it gets hot. I think we're familiar with that. Squash the universe, it gets hot. So in the past, when the universe was squashed, it was hot. And as it's expanded, there's been nowhere for the heat to go. It just fills the whole universe. And the temperature of that is now about just under 3 degrees above absolute zero. And it just bathes the universe, and you can detect it partly from the ground, but better from space. And the interpretation of that is that it's a radiation which has passed more or less unchanged since about 380,000 years after the beginning. So this is the, if you like, the fading afterglow of the fiery birth of the universe. And the little spots you see there, so this is a satellite image, a thermal map of the sky made by a satellite. There have been a number of them, the most recent called the Planck satellite from the European Space Agency. And the little the red and blue dots represent slightly warmer or cooler patches in the sky. And that's essential because those little patches became, those primordial irregularities became the seeds around which galaxies formed by gravitational attraction. So if that slight variation had not been imprinted on the universe at the outset, we wouldn't be here because there would be no galaxies and no stars and no people. So that's a really important part at the beginning. Now, of course, 380,000 years sounds like an early time in cosmological terms, 13.8 billion years, but people want to go back further. How far back can we go with our present understanding of physics? Well, one way that we can probe the physics of the early universe is with this machine called the Large Hadron Collider at CERN near Geneva. This is an €8 billion project which is famous for having created the Higgs boson a couple of years ago, and I'm sure you've heard about that. That was the reason it was built. But you can ask the question, how early in the history of the universe is this machine probing? Now, it circulates protons, counter-rotating protons, and they smash together at very high energy. And so, just for a brief moment, they're recreating the conditions that would have existed in the universe a split second after the Big Bang. And when I say a split second, I can be quite precise about that, about 1 trillionth of a second after the Big Bang. So we can directly, in the lab, recreate a little patch of what the universe was like, a trillionth of a second after the beginning. Now, trillionth doesn't sound very long time in human terms, but actually in particle physics terms, it's still a pretty long time. There are processes in particle accelerators that are a trillionth of a second that can be measured. And the ultimate limit of time, the so-called Planck time, goes back, well, I've lost track of the trillions, but 10 to the power minus 43 seconds. So that's going back a lot further. And that's on theoretical grounds, like the sort of fundamental unit of time that we care about. And so here's a picture from inside the tube. And so this is as far back as we can take it with experiment, but by theory, of course. Theory costs nothing, doesn't cost 8 billion euros to think about this. We want to know, well, can we go back to like the first moment? And was it indeed a first moment, or did something happen? You see, of course, everyone wants to know this. It says before the big boing, what was there? Well, let me just come back to this idea of Newton. So if we think that the universe began at some particular moment in the past, then the simplest way of thinking about it is that, well, sure enough, time stretches back forever to minus infinity, but at some particular moment, I'm calling it C, the universe began, switched on, exploded into existence. So that before that, there's nothing, and then after it, there's a universe. And so we've got before creation and after creation. And that's the sort of naive view that you might have. And it's a view that is a very ancient one, that somehow for all of eternity nothing happened, and then there was a universe. And there are obvious problems with that. You want to know, well, what caused that event? And there are really only two answers: physical processes or God. And each of these comes with their own problems, because if it's a physical process, and there's been an infinite amount of time for that physical process to do its thing, why didn't it do it an infinite time ago? Just seems a very strange idea. But theology is in the same predicament, and in fact, the early Christian theologians were taunted by their pagan detractors who believed in the cyclicity of time, as we have heard so eloquently in Ansi's talk earlier, the notion of the cyclic time. And here we have the linear time of Judaism, Islam and Christianity, this linear time. So what was God doing before God created the universe at this moment C? And the quick answer was busy creating hell for the likes of you, who were Christians. But Augustine, whose name has come up many times, and I'm going to use another quote, I think had the right answer. He wrote that the world was made with time and not in time. And notice the distinction, because now when we say there was nothing before the first moment, I'm calling the Big Bang, what we mean is not empty space. We mean no space, no time. Time itself began with the Big Bang. And it's curious that when cosmologists make the statement, well, time began with the Big Bang, so it's meaningless to ask what happened before it, they're often accused of trickery. I get this all the time. People will say to me, oh, you scientists think you're so clever, but you don't know what happened before the Big Bang, do you? And if I say, well, quite likely nothing happened before the Big Bang was the origin of time, they think, oh, this is some sort of play on words. But then they say, well, I don't understand what that means. Something must have happened. They had trouble with it. And I say, it's a very ancient idea. It goes back to Augustine, at least, back that far. That the world was made with time and not in time. Time is part of physical existence. So that is coming closest to the modern view of the origin of time, the view to which we owe Einstein. It was Einstein who gave us the general theory of relativity, 100 years old last year. And it's that describes the coming into being of a universe with a beginning of time. Time can have a beginning. It's often called a singularity. Mathematical treatment of this means that there are infinite quantities at the beginning, but it very definitely predicts that time can have a beginning. Now, whether that is in fact the case is another matter. Let's see how much time I have to explain the alternative. So if the Big Bang is the beginning of time, so it sort of makes it look like the universe is coming from nothing, and what exactly does that mean, and how do we understand it. And I'd just like to give you one particular interpretation. This was fashionable about 30 years ago, due to Stephen Hawking and Jim Hartle. So I'll tell you about that, and then I'll tell you about the more recent thinking. But this is a particular way of doing it. So the problem is this. The problem when I was a student is if there was a Big Bang that was the beginning of space and time, that looks like an event without a cause. It looks like a magic moment. The laws of physics apply after the Big Bang, but to the Big Bang itself, that lies beyond the scope of physics. Physical law cannot deal with that beginning. And Stephen Hawking set out to remedy that by trying to bring the originating event, the beginning of the universe, within the scope of the laws of physics. And this is how he did it, and this is a sort of tricky one, and this is really a cartoon version. I'd like to talk about space and time. And so space I'm going to draw horizontally, and time vertically. That's quite a conventional thing. And so what is this? This is one dimension of space, and if you can imagine that it maybe goes on forever over there and over there, so this line would have no end. But then it's hard to do the picture, so I'm going to assume that space is actually finite, it's closed. Now, I'm showing, of course, here only one dimension of space. If you wanted the two-dimensional version of this, it would be a sphere. And if you wanted the three-dimensional version, and we do live in three dimensions, it's called a hypersphere. Mathematicians understand it very well. It's finite volume, but no edge or boundary. Well, we don't need to dwell on that, because what I want to do is talk not about space, but time. And if the universe is expanding, well then that's getting bigger. And in the past it was smaller. And it's very schematic. And then we might think, well, can we go back to a point when space had shrunk down to nothing? Yes, that's the Big Bang. The origin of space, you see, comes into existence there. And the origin of time as well. So that's the picture I've been telling you about. But in the 1960s, that was just a magic moment. Just nobody could say anything about that apex there, that first point. Once space was there, once time was there, then the laws of physics could apply. And so what Hawking did was, and of course down here is literally nothing, no space, no time, no matter, no energy, no thing. So literally nothing. And what Hawking suggested, and now of course I'm grossly simplifying what he actually proposed, which was appealing to quantum physics applied to the universe as a whole, a subject called quantum cosmology. So this is quantum space and time. What it can, well, the one thing I will just say, because we heard already about Heisenberg's uncertainty principle, and what this says is in quantum physics, every physical quantity has some fuzziness or uncertainty associated with it. And if you apply that to space and time, well, Einstein already told us that space and time are really linked at a fundamental level, and we really just talk about space-time. Quantum physics, when applied to space-time, is even stranger, because what it's saying is that little intervals of time and little distances in space can sometimes get confused, and time can sometimes think it's space, and space can sometimes think it's time. These things are fuzzed out, so the separate identities. In daily life, we would never confuse an interval of time with a distance in space. We'd never confuse a centimetre with a second. They're very distinctive quantities. But down at that level I told you about, the Planck time, 10 to the minus 43 seconds, and the Planck distance, 10 to the minus 33 centimetres, down at that level, quantum mechanics blurs the separate identity of space and time. And so then it's possible to round off that apex like that, and that's what Hawking was proposing, that's what quantum mechanics does for you. And what does this mean in words? What it really means is that down here, as it were at the beginning, there is no time. There are just 4 space dimensions, and one of these space dimensions slowly, but when I say slowly I mean it takes 10 to the minus 43 seconds, slowly turns into time. So time emerges from space in a continuous manner. But there's no first moment. There's no magic moment, no sudden switching on of the universe. It's sort of self-contained, and so there's nothing before it. So we have what seems like two contradictory statements. On the one hand, the universe has not existed forever and ever, but on the other hand, there was no first moment. And that's because quantum mechanics blurs out moments and intervals of space. So that sort of gets around the problem. Can we think of a universe that comes into being in accordance with the laws of physics without there being some special singular first moment? And the answer is yes. That may not be what happened, of course, but it shows it's possible to have an understanding of the origin of time which doesn't require anything very, very peculiar to happen at the beginning. Nothing transcending any laws. Now, of course, this works only if the laws of physics somehow already exist. And I don't mean that the laws were there before the Big Bang, because there was no before. So they're not prior in time, but they are ontologically prior, to put it in philosophical terms, that they underpin the workings of the universe. So you can buy into this Hartle-Hawking version of the coming into being of the universe if you subscribe to the idea that the laws of physics transcend space and time and somehow exist, like mathematics, in some Platonic realm outside of time, that they are eternal laws. And that was indeed the view that Newton had. So given the laws, the universe can come into being, according to this picture. Now, the conventional view is that the laws themselves were just imprinted on the universe at the outset, or, as I've said, might be eternal. And this raises the whole question, which I'm not going to get into here, about where the laws come from. And the conventional scientific view is you just don't ask that question. The laws exist as brute facts. There's no reason for why they are as they are, or why there are any laws, and that it's not the job of a scientist to ask that. And I'm grateful to Sean Carroll, a cosmologist who writes popular books. In answer to an essay I wrote in the New York Times about how unsatisfactory this was, said, no, it's not. He's a scientist. He said there's a chain of explanations concerning things that happen in the universe, which ultimately reaches to the fundamental laws of nature and stops. Well, is that bad? No, he says, at the end of the day, the laws are what they are, and that's okay. I'm happy to take the universe just as we find it. In other words, he's not questioning where the laws come from or why they already exist. So this reminds us of the Tower of Turtles problem. We push back our explanation further and further and further. You probably know the story. I'll just say it again very briefly about a lecture of this sort, in which the lecturer is challenged by someone standing at the back saying, everything you're talking about is wrong, because I know how the universe is put together. It's the world is standing on the back of an elephant that's standing on the back of a turtle, to which the lecturer replies, and what is the turtle standing on? And the interrupter says, you may be very clever, but you can't fool me, its turtle is all the way down. And so the problem with whether we're trying to evoke science or theology to explain the mystery of existence is, where do we stop? What is the base of that tower? There could, of course, be a super turtle that holds everything up. And in theology, there's a long tradition of trying to define what is called a necessary being. That is a being whose non-existence will be a logical absurdity. If you could complete that dream of showing the existence of a necessary being, then that might give you the basis of an explanation. Of course, whether that necessary being bears any relation to the God of traditional religion is another matter entirely. It's a very abstract concept. But most theologians have abandoned the idea necessity underpinning the contingency of our universe as it is. And so we're left with things in a rather unsatisfactory state. That either you accept God or the laws of physics or something else, some other principle, as simply true, and we know not why, has no explanation. It exists for no particular reason. Or you struggle to try to find some way of explaining why things have to be as they are. It's very hard, because if you found a reason why the universe had to exist in the form that it does, then it would be very strange to think why it couldn't be otherwise, why everything about existence has to be as it is. Somehow, and that's not the view of classical Christian theology, which is that the world does not have to be as it is, doesn't even have to exist. It's a free act of creation by a loving deity. So that's the sort of problem that we run into. I just want to mention, because I've said several times that this view of the origin of the universe as the origin of time was fashionable for a long time, but now some people question it, and I'll just tell you a little bit about that. How much longer do I have?
10 minutes.
Because I've got to do the end of the universe somehow, but that's quick.
10 minutes.
Okay. So, is it the case that the Big Bang was the beginning of everything? Well, not everybody these days agrees with that, and there's a general point to be made here, that if you are persuaded that the origin of the universe was a natural event, not a supernatural event, a natural physical process, as Hawking was attempting to do, then anything that is natural, if it can happen once, it can surely happen again, and again, and again, and again. And so you're led to believe that there wouldn't be just one Big Bang, but an unlimited number of Big Bangs scattered throughout space and time. And that is a view that is now very fashionable, sometimes called the multiverse view. The idea is that what we've all along been calling the universe, this thing out here, very big, but it's just an infinitesimal fragment of what actually exists, which is this vast assemblage of universes that collectively we call the multiverse. There's one particular model of that, not this, I mean this is a cartoon, but of course if you're going to believe in this idea, you have to have a universe generating mechanism. There has to be a bigger system that can make universes by some physical process. And the one that's, the one that's fashionable, I should just mention for those who may follow cosmology, is called eternal inflation. And it's due to Andre Lindy now at Stanford University. And according to that, the big superstructure is eternal. It has no beginning and no end. Our universe is like a bubble that appears in this eternally expanding entity, and there are other bubbles appearing in other regions of space and time. We're confined within our bubble, so the existence of the others is really just conjectural. So that we combine here, in a sense, the best of both worlds. Our own universe has a finite lifetime. It has a beginning and a middle, and maybe an end, as I'll tell you in a moment. So there's a cosmic story to tell. Each bubble has its own cosmic narrative. So we can tell the story of the universe, the greatest story ever told. There it is, but it's not everything that exists. And so if you go into this bigger system, there are other universes and other bubbles, and the bigger system itself is eternal. It has no beginning and no end. But it does have laws. You see, you still need to have laws of physics to make universes. In this bigger system, this eternally inflating system, nobody can tell you why it is as it is. Just because something has always existed doesn't explain why it is so. That's a big problem about any attempt to explain the universe. You can either have it begin at some time, or it never. It's been there forever. Just because something exists forever and ever, it doesn't mean you've explained it. You don't get around the problem of, how do you explain the Big Bang? You don't get around that by saying there wasn't a Big Bang. The universe has always existed. Well, why? Why has it always existed in that form? Why not some other universe or multiverse? So you see the problem is just shoved off to minus infinity. So let me just spend a few moments talking about the end of the universe. And just very briefly, so this is quite easy to follow, the universe is expanding, I told you that, and for a very long time it looked like you had three choices. One is that if it didn't expand fast enough, it would reach some maximum size and fall back to a big crunch, a big bang in reverse. The other is that it's got plenty of oomph, and everything will fly apart and go on until the universe is more or less empty. And the third one is that there's a sort of critical dividing line where the universe will always be expanding at a slower rate, always decelerating, but still go on expanding forever. And those were the three choices when I was a student. And of course, astronomers wanted to know, well, which is the case for our universe. Since then, things have changed a bit because the observations in the last 10 years suggest that actually this is the pattern of expansion. It's speeding up, and that is due to something which is usually called dark energy. It's a sort of cosmic propulsion term. Be happy to explain that in question time if you want more. But the upshot is it acts like anti-gravity, makes the universe expand faster and faster. So for a few billion years after the Big Bang, it began explosively fast, and then it slowed down, and then it sort of dithered, and then it's speeding up again for about the last 5 or 6 billion years. And that seems to be how things are. And so Big Crunch doesn't seem to be on the agenda anymore. But now there's another possibility, which, by the way, I should just explain that this dark energy is actually 3/4 of the stuff of the universe. People say they don't know what it is. It's actually the energy of empty space. So you might want to ask me question time, why should empty space have any energy at all? And the simple answer is, well, why not? It looks like it does, and it adds up to 3/4 of the mass of the universe. It's actually the mass of empty space itself. Our stuff, that is atoms and things like that, 4% of the total. See? So we're just like a cosmic afterthought. All the things that we thought were the universe, like stars and planets, gas and dust and all that stuff, is only 4%. And there's another component, is dark matter, and this is going to be particles of some sort, which haven't yet been discovered, but maybe very soon. That's the makeup of the universe. But now, this dark energy, if it stays constant, the universe will go on expanding at an accelerating rate, but that rate of acceleration is fixed. So what that means is the universe will double in size in a fixed period of time. So every 10 billion years, it's twice the size, and 10 billion years after that, it's twice that size. So it's like Moore's law in computer science. You know, it's a sort of doubling time. But we don't know that that dark energy is going to stay the same. And the current observations are consistent with it possibly getting stronger and stronger. And if so, that rate of acceleration will get faster and faster and faster until it becomes infinitely fast. And that represents what mathematicians call a singularity. I mentioned that earlier, but in terms of infinitely compressed. This is infinitely expanding. And that's often called the Big Rip, because in effect what it means is space itself is ripped apart, whatever that means. And that is one way that the universe could end in the future, could end in a Big Rip. There we are, Armageddon in about another 50 billion years. So everything expands faster and faster. Of course, the Earth would still be around. But you can imagine that if you were there to witness this, the planets would be ripped apart by this huge propulsive force, and then the atoms would be ripped apart, and then the nuclei would be ripped apart, and then eventually space would be ripped apart a split second later. So that's one possible way it could all come to an end. So what we've got then is the old-fashioned idea of collapse to a big crunch, probably not going to happen, could expand forever into dark emptiness, which is the death by boredom, really, or the Big Rip. And at this stage, we simply don't know which of these is on offer, but it does seem to cover all of the contingencies. So I want to bring this to an end, as one must, with a quote from Einstein, on him so much of what I've been saying. It depends on his work. He echoes here a sentiment that, well, I should say the other way around, he expresses a sentiment that I echo, that humans are not merely observers of the universe. They come to understand how the universe works through this amazing thing we call science. And the way he expressed it was the most incomprehensible thing about the universe is that it's comprehensible. And so that's the take-home message, because we don't know, we can guess, but we can get evidence for whether there was a beginning of time and whether there will be an end of time. But as I've tried to stress, that ultimately all of this is based on science, and science is based on laws, and we have to ask, where do those laws come from? That's one question. But why is it that we human beings are so privileged that we can come to understand those laws and understand how the universe is put together? And for me, the ultimate mystery of existence is the fact that we have the ability to unravel the secrets of nature in that way. And so that seems to be a good point to start. I'm happy to take questions, but I think we'll probably do that after the break. Is that all right? Thank you.